Welcome to the deep dive. Today, we're cutting straight through the hype and getting into the real technical heart of the Olmo 3 model family. This is a huge open release from the Allen Institute for AI.
It really is. And our mission here is to peel back the layers for you, to really get into the engineering, the training methodology, the whole recipe.
Exactly. This isn't just about the models, it's about how they were built. So they released 4 distinct models, which is already an interesting choice.
Right. And they all come from one common base, but they're specialized. That's a key technical step up from their previous releases.
Okay, so let's break them down. First, you have the foundation, the Olmo 3 base. Pretty straightforward.
Yep. But then it gets interesting. You have Olmo 3 Think, which is engineered specifically for that heavy-duty, long-form reasoning.
The kind that produces those thinking traces to show its work.
Exactly. And on the flip side of that, for efficiency, there's Olmo 3 Instruct.
And that one's more for general chat function calling. Basically, the things you'd want to be fast and short in a real-world application.
Right. And then there's the last one, Olmo 3 RL0. And this one is, I think, a really important contribution.
It's a fully open base model trained with reinforcement learning, right, to basically create an open benchmark.
Precisely. It tackles that whole data contamination problem you see in closed RL systems. It's a vital piece of the puzzle for the community.
So what's the thread that ties all of these together?
Compute efficiency. The whole challenge they took on was, can we close the gap with state-of-the-art models, like, say, Quinn 3, but on way, way fewer tokens?
And the paper says the Think model did this with roughly 6 times fewer tokens.
6 times. That means there's basically no room for error. Every single token has to count. It has to deliver maximum signal.
So let's dig into how they did that. We'll look at the 3 big stages: pre-training, mid-training, and then the long context extension. Let's start at the beginning. Pre-training and data mastery.
Okay. So architecturally, they made a pretty straightforward but really important first decision.
They stuck with the Olmo 2 architecture.
They did, a decoder-only transformer. But they immediately doubled the pre-training context window, from 4096 tokens up to 8192.
Which sets the stage for scaling up to long context later on.
It's the essential first step, and the scale here is just vast. They trained for up to 5.9 trillion tokens on their Dolma 3 mix.
Wow. At that scale, speed is everything. So how did they manage the infrastructure, the throughput?
Infrastructure efficiency was paramount. They were hitting about 7,700 tokens per second per GPU for the 7B model.
That's flying.
It is. And they did it using hybrid sharded data parallelism, HSDP, through PyTorch FSDP2 on a cluster of 20 and 24 H100s.
Okay, so let's do a quick neural signal check here. For someone training their own models, why is hybrid sharding so important at that scale? Why not just regular data parallelism?
Well, when you've got a 10 and 24 GPUs, your biggest enemy is communication latency. HSDP is key because it's smart about what it communicates where. It keeps all the really heavy traffic, like syncing gradients, inside the node.
So it's not clogging up the whole data center network.
Exactly. It cuts down that expensive, slow, cross-network traffic, which is just critical when you're pushing trillions of tokens. It's a direct path to faster iteration and, lower costs.
Makes sense.
Yeah.
But all that speed is useless if the data is dirty.
Yeah.
Which brings us to how they handle the data itself. Common Crawl is notoriously full of junk.
And they were obsessed with cleaning it. They engineered this incredibly aggressive 3-stage deduplication process with their own tool, Duplodocus.
Stage 1 was the easy part, I guess.
Yeah.
Exact duplicate.
Yeah, a broad sweep, hash-based, and that alone got rid of almost 2/3 of the pool. The paper says 67%.
Wow.
Then stage 2 was fuzzy matching, min hash. This is for, the same article copied on 50 different websites with just a different header.
Right.
They set that to an 80% similarity threshold, and boom, another 23% of the document's gone.
But the really novel part, the one that I think makes all the difference, was stage 3, this fuzzy suffix array-based substring deduplication.
That is what gave them the real edge on token efficiency. It's designed to find all that repeated boilerplate text inside documents. Think legal disclaimers, website menus, stuff that normal hashing misses.
And it targeted substrings of 500 bytes or more.
Exactly. And that one stage, by itself, reduced the web corpus by 75%. The result is a data set with just dramatically higher information density.
That is an insane level of cleaning. And after all that, they didn't just mix it all together. They used something called quality-aware upsampling.
Right. This is all about maximizing the signal from their best data. So instead of a flat filter, they split the data into 480 different subsets.
24 topics by 20 quality tiers, I think.
That's it. And then they use these upsampling curves so that the highest quality stuff, like top-tier academic papers, could be repeated up to 7 times in the training data.
Squeezing every last drop of value out of the good stuff.
That's just smart resource management.
Okay, so pre-training sets the foundation with super efficient infrastructure and surgically clean data. Let's move to the next stage. Iterative refinement in mid-training. How do you steer the model once it's built?
Well, you need a better steering wheel than just standard public benchmarks. They found those were often too noisy, so their solution was to build their own custom benchmark suite, Olmo Base Evil.
So neural signal check number 2. Why invent a whole new evil suite? There are tons out there.
It comes down to statistics, really. They found that in their small, iterative test runs, the tiny differences you see in standard benchmark scores could just be noise. You can't make good decisions if you can't trust the signal.
So Olmo Base Evil fixed that.
It helped a lot. It aggregates scores over task clusters, like all the multi-choice science questions together, and it calculates a signal-to-noise ratio for each task. So they could just ignore or downweight the noisiest metrics.
And they use this high-fidelity tool for what they call distributed exploration.
Yeah, running these lightweight 10 billion token microanneal runs to quickly test new synthetic data sources like tiny math or crane code.
And doing that quickly exposed some really critical domain trade-offs, didn't it?
Oh, absolutely. The classic trade-off every model trainer faces. They found that if they cranked up the weight on math and code data, those scores went way up.
Oh, go ahead.
But it came at a direct, measurable cost to performance on things like multi-choice QA and general Q&A. They literally had to budget the model's capacity in their final mix.
That balancing act is the real art form here. Yeah. But they also found something really surprising about using instruction data during this phase.
Yes. This was fascinating. You'd think that data, instruction following and thinking traces is purely for post-training and alignment.
But they found it actually improved the base model's performance before any post-training even started.
It suggests those high-quality structured sequences aren't just for alignment, they're capability enhancers. They're injecting a kind of structural reasoning deep into the pre-training phase itself.
But this stage also had a catastrophic failure. A big lesson about tokenizer integrity.
A huge one. The moment they tried to introduce special chat tokens like imstart into the mid-training mix, the model just fell apart.
How badly?
I mean, on the GSM-8K math benchmark, accuracy went from nearly 50% straight to 0.
So 0. Wow. What happened?
The model just started spitting out those special tokens during inference, which completely broke the evaluation parser. The takeaway was crystal clear. Keep special tokens out until the SFT phase.
Protect the integrity of that foundational vocabulary. Okay, let's move to long context scaling. The model is at 8K context, but everyone needs more. They pushed it to 64K.
A massive jump and a massive computational challenge. They did it with a pretty short extension phase, another 50 to 100 billion tokens.
And the key technique here was a specific kind of row piece scaling, right?
Yarn. But they were very particular about it. They applied it only to the full attention layers to keep things stable and get the best performance.
And I assume the data for this phase had to be special. You can't just use more web text.
Not if you want the model to actually use the long context. The mix was heavy on things like OCR'd science PDFs and synthetic tasks designed to force information extraction over really long distances.
Now, managing a 64K sequence length, the memory cost alone must be insane. How did they handle that on the infrastructure side?
2 main tricks. First was data prep, best fit document packing, instead of just chopping up documents and leaving lots of wasted padding at the end.
They packed multiple smaller documents into a single 64K window.
Exactly. It reduces waste and actually improves performance on long context benchmarks. But the second part was distributing the load itself.
And that's context parallelism.
Right. Training at 64K required 8-way context parallelism. You can think of it as taking that huge 64K sequence and splitting the work so that each H100 GPU only has to deal with an 8K chunk of it.
So you're splitting the memory load across the devices.
You have to. Without that kind of parallelism, it's basically impossible to train context that large because you'll just run out of VRAM.
Okay, that makes perfect sense. Let's get to our final technical section, advanced tuning recipes and the OlmoRL breakthroughs. After the base model, we get the specialized think and instruct models.
And they go through 3 more stages: supervised fine-tuning, SFT, then direct preference optimization, DPO, and finally reinforcement learning with verifiable rewards, or RLVR.
The DPO stage here was interesting. They said traditional SFT had kind of hit a wall.
It had saturated, they couldn't squeeze any more general capability out of it, so they pivoted DPO from being just about alignment to something they call contrastive delta learning.
Using it to gain new capabilities, not just follow preferences.
That's the idea. They would pair a really high-quality completion, sometimes from a more powerful model like Qwen 3, with a clearly weaker one. This creates a huge quality delta, a really sharp contrastive signal.
Which lets DPO push the model's reasoning abilities further than just imitating good examples.
Exactly. Now let's talk about the infrastructure for the RL stage, the OlmoRL framework. They got a 4 times speed up in training efficiency. This is a game changer.
How? What were the breakthroughs?
It's all about eliminating GPU idle time. The first big win was continuous batching. Normally, in RL, you have a static batch. If one generation finishes early, that GPU slot just sits there, idle, wasting compute.
Like a train waiting for every last passenger before it can leave.
A perfect analogy. And they calculated that waste could be up to 54% of your compute time. Continuous batching just immediately fills that empty slot with a new job. Maximum utilization.
What was the next big gain?
In-flight updates. This is a big one. Usually when the policy gets updated, all the actors have to stop, dump their KV caches, and sync up. It's a huge pause.
But they found a way around that.
They did. They update the learner weights asynchronously. The actors can just keep on generating data while the update happens in the background. They said this had the single biggest impact on throughput.
And the last piece was optimizing the samples themselves. Active sampling.
Yeah, this is about making sure you're only learning from useful data. It filters out samples that have zero gradient advantage, the ones that provide no learning signal, and pulls in new ones to make sure the batch is always full of things that will actually help the policy improve.
So to summarize the engineering here, it's just efficiency at every single layer. From surgically clean data at the start
to high-fidelity evaluation signals in the middle.
And finally, this incredibly high-throughput asynchronous RL framework at the end.
And don't forget the final little trick, model souping, merging checkpoints. For their 32B model, they found that just averaging the weights of 2 separate mid-training runs gave them a nice performance boost, especially in math.
A super practical solution for smoothing out training variance, which brings us to our final provocative thought, and it comes from that Olmo 3 RL0 release.
Right. So RL0 was trained on a mix of domains math, code, instruction following. And what they found was that training on this multi-domain mix actually gave them a lower overall training reward than training on just one of those domains.
But it generalized better on downstream tasks.
Precisely, which reveals this deep technical trade-off. It raises the question, how do you actually design reward functions for these complex, multi-objective settings? How do you encourage broad generalization without the model just? Reward hacking the easiest or highest reward domain and over-specializing.
That's a fascinating problem, the tension between specialized peak performance and broad, robust generalization.
It really is. It forces you to rethink what a good reward signal even looks like in a multitask world. The RL0 framework is now the perfect open testbed to start answering that question.
And that seems like the perfect place to leave it. That concludes our technical deep dive into the engineering breakthroughs of the Olmo 3 model family.